Yes, dear students, in the last class, we have discussed magnetic effect and Lorentz force and force acting on the two parallel current carrying conductors with the help of concept of Fleming's left-hand rule. Today, we will discuss new topic, torque or moment of magnetic force experienced by a current carrying loop when placed in an external uniform magnetic field. So far in the last class, we have discussed that whenever a current carrying conductor placed in external magnetic field, it experiences force. The magnitude of force is given by F equal to ILB sine theta. So here we will apply the same concept here, taking the rectangular loop with four sides as if current carrying conductors. And we will calculate the magnetic force acting on each arms of the coil due to current carrying conductor, due to current flowing through it. So you see in the figure that a rectangular current carrying loop in which current flows in anti-clockwise sense and magnetic field is in the direction, say along x-axis. And this figure is in the xy plane. So here, if you consider theta as the angle between the plane of the loop and the direction of magnetic field, the axis of the coil is perpendicular to the magnetic field. This is the axis of the coil. This is the axis of the coil. And so we will calculate magnetic force on each of the arm due to the current flowing through each arm. So try to understand. First of all, we calculate magnetic force on the arm S to P. Current flows in this way. You see here. Current flows in this way. And this current makes an angle theta with the magnetic field. So magnetic force acting on this arm is FSP equal to ILB sine theta. So here, this is the current I flowing through this arm, and B is the length of PS, that is width, breadth of rectangular coil, rectangular loop. So here it is B. As in the previous section, I have discussed that magnetic force equal to IL cross B, I into L cross B. So here in place of L, we take here breadth, that is the breadth of this rectangular loop. So I is taken outside the bracket and vector B into vector capital B, that is magnetic field. B is the length of the PS and capital B is the magnetic field. So magnitude of magnetic force acting on this arm is given as IB sine IB and capital B sine theta, where I is the current through the arm PS or SP. Now we take the magnetic force acting on the opposite arm which is opposite to the PS, that is QR. In this section, current flows in this part in opposite direction in comparison to this part. Here current flows from S to B, S to P, and here Q to R. That is opposite to that of the this arm. But angle or orientation of this section of the arms and this section of arm is the same. Therefore, magnetic force acting on this arm will be FQR equal to IB B sin theta. Only difference will be that the direction of force will be opposite to that of this one. If you apply on this conductor Fleming's left hand rule, you will see that the force on this conductor will be in this direction. That is, put your middle finger along the length of S to P and forefinger along this one, then your thumb will be pointed in this direction, giving the force SP. Similarly, apply Fleming's left hand rule on this part of the wire. You will see that forefinger with your forefinger pointed in this direction and your middle finger pointed in this direction. You will see that the force QR acting on this arm will be in this direction. So vector sum of this force SP and QR will be 0 because the two forces are opposite to each other. Their directions are opposite to each other, but their magnitude is same. That is IB and capital B sin theta. IB capital B sin theta. Magnitude is same, but their direction is opposite. Therefore, their vector sum becomes 0. So net force acting on this arm and this arm is 0. Now let us calculate the magnetic force acting on this arm and this arm, that is longer arm of the coil. So here you will see that force SP and QR are equal in magnitude but opposite in direction, and they cancel out each other. That's all. Moreover, they act along the same line of axis and hence do not produce any torque. So torque produced by these two forces are 0. Now come to the point on the longer arm, that is PQ and RS. So magnetic force acting on this section of the conductor PQ equal to FPQ equal to I into L cross B. This is the length of the rectangular coil. L is the length of the rectangular coil. Here you see. So bold here, this is in bold. This is current I. And this is a small letter L, which indicates the length of the rectangular coil. So force is equal to this. Here we see that current and magnetic field makes an angle of 90 degree. That is length of this arm and magnetic field makes an angle of 90 degree. Therefore, here F magnitude of magnetic force acting on this arm equal to I into L into B sine 90 degree equal to ILB. That is maximum force experienced by the longer arm, and zero torque experienced by this arm. So maximum force experienced by this arm, and if you apply the Fleming's left hand rule, that is placing your middle finger in this direction along the length of the conductor and directed in the direction of arrow, that is current, and forefinger in this direction, then you will see that your thumb will be directed in this direction. That will give the direction of force F, PQ. Similarly, we have to determine magnetic force acting on the arm, RS. Same current flows through this arm and same situation will be there. Only difference is that current in this arm flows in opposite sense of these arms. So magnetic force will be opposite to that of this force. So, but magnitude will remain same because length of this arm and length of this arm is same. Current flowing through this arm and this arm is same. Only current's direction is different, and magnetic field for both the arm is same. That's why the two arm will experience a force in equal and opposite direction. So these two force FPQ and FRS forms couple of force. So whenever couple of force act on anything, it produces turning effect. That's why this coil will tends to rotate in anti-clockwise sense in this way. So you see here magnitude of the force experienced by the two longer arm equal to ILB, but their direction is opposite to one another. In this case, this force will be directed into the plane of the figure, and in this case, this force is directed in out of the plane of the figure. So force FPQ and FRS being equal in magnitude but opposite in direction, cancel out each other and do not produce any translational motion. So these two forces are directed equal and opposite direction, that is directed opposite to each other. Therefore, net sum of net translational effect produced by these force is 0. But rotational effect will be non-zero. But they act along different line of action and hence produce moment of force, that is torque about the axis of the coil, and hence coil will starts rotating. So you see here, so net torque produced by the current flowing in the conductor or coil due to magnetic field can be obtained as the vector sum of the torque produced by the individual longer arm. So you see here torque produced by the longer arm PQ is just equal to product of magnitude of force and perpendicular distance from the axis of rotation. So you see here, this is the axis of rotation, and from here perpendicular distance is this one. You can say that here Pn, this is the perpendicular distance, P to N. This is the perpendicular distance. So you can calculate with respect to that one. So here we see that torque equal to ILB into a small b, because if you take this one and we have to calculate Pn, then in right angle triangle PSN, this act as a base and this act as a hypotenuse. So base upon hypotenuse equal to cos theta, that is Pn is to Ps equal to cos theta. Therefore Pn equal to Ps cos theta, and Ps is nothing but what? B. So we can say B cos theta. So in place of Pn we write here B cos theta. So and FPQ equal to ILB. So ILB into B cos theta, that is ILB B cos theta. So L into B, that is length into width, equal to area, that is area of this loop, area of this coil. So this area is represented by capital A, and this is magnetic field, capital B is magnetic field. So we have torque equal to IAB cos theta. Now for n turns of the coil, this is for single turns, I into A into B cos theta. So for n turns of the coil, if there is n turns, then area will be n times, that is n into I into A into B cos theta, where is the n is the number of turns. Then I'm now trying to understand if phi is the angle between the normal to the coil, you see here, this is the coil and plane of the coil, uh, n cap here, n cap is the normal to the plane of the coil. So if phi is the angle between normal to the coil and the direction of magnetic field, then so so you must add this, because theta plus phi equal to 90 degree, because this is perpendicular to the plane of the coil. So theta equal to 90 minus phi. So cos 90 minus phi equal to cos 90 minus phi equal to sin phi. Therefore, tau equal to NIAB sin phi. So now we can write here I into A equal to magnetic dipole moment of magnetic field. So here I into A is M and N into I A equal to net moment, magnetic moment. So then we can write here tau equal to M cross B. You will see here. Now try to understand first. One must be very careful in using the formula in terms of cos or sin, since it depends on the angle taken, whether with the plane of the coil or with the normal of the coil. Either we take angle with the plane of the coil or with the normal of the coil. So you see here in the vector form, tau equal to NIAB sin phi. So we can write here, take this one NIA as one single quantity, and this single quantity is denoted by M and called magnetic moment, and B is another vector quantity. So M cross B will be vector forms. So try to understand here. Tau equal to NIAB sin phi, it is well known. So in vector form, NIAB sin phi into n cap, where n cap is the unit vector perpendicular to the plane of the figure or plane of the coil. So where n is the unit vector normal to the plane of the loop. So taking a scalar quantity outside, n into I, n is the number of turns and I is the current. This is the scalar quantity. And area vector inside the bracket. So area vector into B. And now if you take this scalar quantity inside, then area vector into Ni is again a vector. And now this vector will be magnetic dipole moment, because in the previous section we have discussed that a current carrying loop acts as a bar magnet, with one face as north pole and other face as south pole. So it acts as a magnetic dipole, and its dipole moment is just equal to product of current and area of the loop. So that is M equal to I into A. So this is nothing but magnetic dipole moment. So N equal to tau equal to N into M cross B. So in case N is equal to 1, that is number of turn is 1, then tau equal to M cross B. And in case of number of turns is N, then tau will be N times that of the single coil. So the coil will rotate in the anti-clockwise sense from the top view according to figure. If one look this coil from top of the figure, or from plane of the from the top from the plane of the figure, then they will observe that coil would rotate in anti-clockwise sense. Okay. The torque acts in the upward direction along the dotted line, that is along the axis of the coil, according to Maxwell's screw rule, or Maxwell's right hand thumb rule. Then if phi is equal to 0, then torque will be 0. And if phi equal to 90 degree, then tau will be maximum, that is NIAB. Now try to understand units. B in Tesla, magnetic field, SI unit of magnetic field in Tesla, and SI unit of current in ampere, area in meter square, then tau in Newton meter. So the above formula for tau can be used for any type of loop, irrespective of its shape. So far we have learned that a current carrying coil will experience a moment of force. That moment of force would depend on area vector and of the coil and magnetic field, and even depend on current flowing through this. More is the current, more will be torque, and also depends on number of turns. If number of turns of the coil increased, then area vector yes, try to understand. Now the same concept would be applied over electric motor, electric generator, and moving coil galvanometer. As we see that a current carrying coil, when placed in external magnetic field, it experiences a torque. So we apply the concept in case of moving coil galvanometer, that is MCZ. Torque experienced by the coil. Look at the figure here. We take two magnets, one with south pole in this face and other with north pole in this face, and in between these two magnets we place a rectangular coil fitted or pivoted over a frame, solid frame, so that it can rotate about. And here pointer would be given. So try to understand that torque experienced by this coil is given by tau equal to NIAB sine phi, as we have derived in the previous case. Now this torque is counterbalanced by the elastic force fitted with this wire, which is twisted. So this elastic force also produces a torque, and we know that elastic force is directly proportional to twisting, angle of twisting. So here tau is proportional to alpha. Alpha is angle of twisting of the wire. So tau equal to K alpha, where K is proportionality constant and also called restoring torque per unit angular twist. And alpha is the angular twist in the wire. If you place the wire fixed and try to rotate, twist it, then a mechanical torque will develop in the wire that will depend on elastic property of the wire. So the magnetic torque produced by the current in the coil and mechanical torque or elastic torque produced due to twisting of the wire will counterbalance each other. Therefore, we will equate the two torque here, NIAB sine phi equal to K alpha. Therefore, I equal to K NIAB sine phi into alpha. So you see here the cage elastic property of the wire. So, and I is the current. So current sensitivity here we have to decide. More if the angular twist is there, more reading will be in the galvanometer, that will be more current will be measured. So if you keep all the things constant, then current is directly proportional to amount of twisting produced in the wire. The factor sin phi can be eliminated by choosing radial magnetic field. If you take radial magnetic field, then this sin phi factor can be eliminated. So try to understand here, torsion head, here you will see here, torsion head, TS terminal screw, M mirror, NS is the pole pieces of the magnet, LS is the leveling screw, here LS is the leveling screw, and PQRS is the rectangular coil that I have already discussed in the previous section. And PVW is the phosphorus bronze wire, because phosphorus bronze wire has twisting effect, elastic properties. So PVW is a phosphorus bronze wire, and this wire gets twisted and hence produce elastic torque in order to counterbalance the torque produced by the current in the coil. Now LS is what? Leveling screw. Here screw is level, and TS is terminal screw. Here you see terminal screw. We can measure it, we can adjust it, terminal screw. And NS is the pole pieces of the magnet, and M is the mirror. So look over, where is M? Here M is the mirror that could help you to calibrate or even show you the twisting produced in the coil. Now in place of this plain circular poles, in order to eliminate this factor sin phi, we replace this uniform field in terms of radial magnetic field. You see here horseshoe north pole and horseshoe south pole. Here magnetic field becomes radial. So that top view PS of the plane of the coil PQRS lies along the magnetic lines of force in whichever position the coil comes to rest in equilibrium. In this situation, in whichever position is the coil, it will be always in equilibrium. That's why sin phi factor is eliminated from this expression. And current part here, current sensitivity can also be described here. First of all, try to understand here. So the angle between the plane of the coil and the magnetic field is 0, because always comes in equilibrium, or the angle between the normal to the plane of the coil and the magnetic field is always 90 degree. So sin phi, that is phi equal to 90 degree, therefore sin 90 equal to 1. So it will be eliminated. That is I equal to K divided by N A B. So here current inversely proportional to number of turns in the coil, inversely proportional to area of the coil, inversely proportional to magnetic field, radial magnetic field, and directly proportional to twisting angle. So here we can say I equal to G alpha, where G equal to K upon N A B, and is called galvanometer constant. This G is called galvanometer constant. So various types of galvanometer can be framed out or made by changing galvanometer constant. So you see here that galvanometer constant can be changed by changing the elastic properties of the wire, or changing number of turns, or magnetic field, or area or size of the coil. Now, so far we have learned this one. Now we have to learn current sensitivity of the galvanometer. What is current sensitivity? So basically, current sensitivity of a galvanometer is defined as the deflection produced in the pointer of the galvanometer per unit current. So deflection is alpha, that is twisting angle, and per unit current. If for a small current there is large deflection, then we can say that galvanometer is more sensitive to even a small current. So current sensitivity of a galvanometer is inversely proportional to elastic property of the wire and directly proportional to number of turns of the coil and directly proportional to area of the loop of the coil and directly proportional to magnetic field. More is the magnetic field, more will be sensitivity. More is the number of turns, more will be sensitivity. More is the area, more will be sensitivity. Less is the elastic property, more will be sensitivity. So far we have learned here current sensitivity. Now we have to learn about voltage sensitivity. So in order to see this expression, if you multiply both sides by R, that is resistance, then I into R becomes V, and here KR. Both sides multiply R by R, resistance of the wire or coil. Then we will have the situation here, current sensitivity when divided by resistance, then becomes voltage sensitivity. And voltage sensitivity when multiplied by resistance becomes current sensitivity. So here, dividing both sides by R, resistance, then this becomes alpha divided by V, and here we will get LAB upon KR. So in this case, we see that voltage sensitivity of the galvanometer is inversely proportional to resistance of the coil, and everything is same. So we can say that voltage sensitivity is just equal to a ratio of current sensitivity and resistance. So voltage sensitivity of a galvanometer is defined as the deflection of galvanometer produced deflection produced in the pointer of galvanometer per unit voltage. So far we have seen that galvanometer has sensitivity, current sensitivity and voltage sensitivity. That galvanometer shows sensitivity towards voltage and towards current. Therefore, a galvanometer can be converted into voltmeter or ammeter. So try to understand how to convert it into voltmeter and ammeter. Okay. Now, let us check. Okay. So, now try to understand conversion of galvanometer to ammeter. In order to convert a galvanometer into ammeter, resistance of galvanometer must be reduced because an ideal ammeter has zero resistance so that it can measure current more accurately. So here we have to reduce the resistance of galvanometer. In order to reduce the resistance of galvanometer, we have to connect very small resistance parallel to the galvanometer, such that resistance of combination would be much smaller in comparison to that of the galvanometer. That's why now this galvanometer would measure current up to maximum accuracy. Galvanometer can be converted into ammeter by shunting it with a very small resistance. That is, shunting means we connect a very small resistance in parallel with the galvanometer in the circuit. So you see here, potential difference across the galvanometer and the shunt resistance are equal because both of them are connected in parallel. Therefore, so potential across shunt resistance is just equal to resistance into current across the shunt, and potential across galvanometer just equal to product of current through galvanometer and resistance of the galvanometer, because both the potential are equal, so these two equated together. So after that we can calculate shunt resistance. You see here the shunt resistance is expressed as Ig into capital G divided by I minus Ig, where I is the net current supplied in the circuit, Ig is the current going through the galvanometer. So shunt resistance can be calculated in order to calculate, convert galvanometer into ammeter. Now, remember that while converting galvanometer into ammeter, we must connect shunt resistance in parallel with the galvanometer. Now, conversion of galvanometer into voltmeter. Just we have to connect resistance in reverse sense of that of the ammeter conversion. So here, while converting galvanometer to voltmeter, galvanometer can be converted into voltmeter by connecting it with a very high resistance in series, because here we want to measure potential, not current. So we can measure accurately potential if we have a high resistance across the galvanometer. So we, in order to increase the, we know that voltmeter has infinitely large resistance, therefore we increase we add an additional resistance which is very high, and connected it in a galvanometer with the galvanometer in series, so that it can measure potential and a very small current passes through it. Okay. So potential difference across the given load resistance is just equal to sum of the potential across the galvanometer and potential difference across the high resistance. So here, as these two are connected in series, therefore potential across this combination is just equal to potential, sum of potential across galvanometer and across this high resistance. So V equal to Ig into G plus R, because same current passes through this. So effective resistance across this combination is G plus R, where G is the resistance of galvanometer. So R equal to, R equal to here V upon Ig minus G. So if Ig is to be lesser, then R will be maximum. So here current through the galvanometer must be smaller and smaller. Even if it is 0, then this resistance will be infinite. So this was the two concept based on the conversion of galvanometer. And now here we have to differentiate, or difference between ammeter and voltmeter we have to learn. Ammeter, it is low resistance instrument. On the other hand, it is a high resistance instrument. Resistance in the ammeter is just equal to product of shunt resistance and galvanometer resistance divided by sum of shunt resistance and galvanometer resistance. It's obtained in case of galvanometer is converted into ammeter. Here, resistance is just equal to G plus R, because the two connected in series. Now, shunt resistance in case of ammeter will be very small. On the other hand, in case of voltmeter, it will be very high. Now, in case of ammeter, it is always connected in series this is wrong. In case of ammeter, shunt resistance is always connected in parallel with the galvanometer. So just you have to understand it well. Just reverse all these things. One thing that you have to remember, ammeter is always connected in series with the circuit. So here it is always connected in series with the circuit such that it can measure maximum value. But voltmeter is always connected in parallel with the circuit or section of the circuit where it can measure the voltage. Now, resistance of an ideal ammeter is 0, while resistance of ideal voltmeter is infinite. So, hello, Abhishek, Prabhat Kumar, roll number this one. Do you have any problem?
No, sir.
Okay. If you have any problem, then you can ask me. No question?
No, sir.
Okay. Now try to understand here. In case of ammeter, resistance must be negligibly 0. That is, for an ideal ammeter, resistance must be 0. For an ideal ammeter, resistance must be infinite. Now, resistance in case of ammeter is less than that of the galvanometer, but resistance in case of voltmeter is more than that of the galvanometer. It is because of this reason, in case of galvanometer, while converting into voltmeter, a shunt resistance connected in parallel with the galvanometer. On the other hand, while it is converted into voltmeter, a resistance, high resistance connected in series with the galvanometer. Now, it is not possible to decrease the range of given ammeter. That means range of ammeters cannot be decreased. But in case of voltmeter, it is possible to decrease the range of given voltmeter by connecting additional resistance. So I think that for today's class, that's all for today. And video lecture of this one will be uploaded on YouTube. Okay. Thank you.
Yes, sir.